Hello, I'm Anna Mackay and today we're looking at the tangent function. So just a quick refresher on where the tangent function comes from. Imagine your unit circle and the tan stands for the word tangent, and it is a tangent drawn to the unit circle once at that point there, at when the degrees is 0 degrees. And you imagine a triangle, a right-angled triangle that is drawn out to that tangent. And tan of theta is the gradient, if I can write that, is the gradient of the slope, or of the line, OP. Also remembering that tan is sine over cos. We're not going to go into much depth now as to why this is the way it is, just remembering that the sine over cos and the tan, the fact that that's a fraction, actually comes from rise over run. So if you were to think about this right-angled triangle, just thinking about the gradient of the line OP in relation to the tangent that it touches, if that line OP is lying flat on the x-axis, what's the gradient of that line? It's 0, and you get that gradient of 0 at 0 degrees. Thinking about when the gradient of that line might be 1, that's when your rise over run is equal, and the only time that happens for sine and cos is at pi on 4 at 45 degrees. So at 45 degrees you would have a tan of 1. And then thinking about as this line continues up until it's nearly vertical, and imagine it extending up to that tangent line and seeing if they touch each other, but at some point they're not going to. And therefore the slope of the line OP would be undefined. And at how many degrees is that? That's at 90 degrees or pi on 2. So at pi on 2, tan is undefined. Let's have a look at the graph of tan now. Here we are. So I said at pi on 2, tan of x is undefined, and that's represented by a vertical asymptote on the graph here. We talked about the fact that at 0 degrees, it also had a slope of 0, and so that's why we have an x-intercept at that point through 0. And the other one we talked about was when tan of x would be 1. So if you went up to the y-axis here and looked across at 1, came across to find out what's your x value there, that would happen at pi on 4. Some facts about tan, just a refresher there that it's sine on cos, and the period of that. So at what point does it repeat itself? It's different to the sine and the cos ones. It is a pi, period of pi as opposed to 2 pi. The range, so thinking about the y values that it can take here, it can take any y values as opposed to sine and cos, which traditionally range between 1 and -1. Vertical asymptotes for every x is equal to pi on 2, and adding on multiples of that to allow for all the periods of pi, and for all integer values is what we've got there. Now some transformations of the tangent function. Just summarising these, the graph of y equals tan bx, so if you have a number there in front of the x, that changes the period, or the horizontal dilation if you like, and it has a scale factor of 1 divided by b. Therefore the period is pi divided by b. Think back to the period of sine and cos. Their period was 2 pi, and the same technique applied. If you had a b value next to x, you took 2 pi and divided it by b. This time round you're taking the period of pi and dividing it by b. So the technique's still the same. And also for horizontal translation, shifts, moves, that if it's a negative c there, that it's the opposite direction to what you might be expecting. So in comparison to tan of x, it's horizontally moved through c units. So some examples here. Without using technology, sketching the graph of tan x plus pi on 4 for the domain of from 0 to 3 pi. So first of all, visualize, what does tan of x look like? So as we've discussed, it has a period of pi Do note though that the period doesn't start at 0 to the first pi. For tan, it goes between negative pi on 2 to positive pi on 2, and that's fine. That's just the uniqueness of tan. And thinking about where the x-intercepts are. So there's one x-intercept per period, and the first one's at 0, the next one's at pi, the next one's at 2 pi. For tan of x plus pi on 4, our vertical asymptotes are going to be at pi on 4, 5 pi on 4, and 9 pi on 4. Thinking about why, this has had a shift to the left. So thinking about these vertical asymptotes, we've got one at pi on 2. If you shift that to the left, a value of pi on 4, you're now going to have your first x-intercept at pi on 4. Think about the other vertical asymptote, shift that, so you've got 3 on 2, 1.5 if you like. If you have 1.5 and you take off a quarter, you're going to end up at 5 quarters. And same for the third one, to make sure you fit it in that domain. And your x-intercepts this time, well, everything again has shifted to the left, 1 quarter, a pi on 4. So this x-intercept at 0, that shifted out of your domain. So you don't have to worry about that one, but the others you do. Pi has now shifted a quarter to the left, so therefore our intercept is at 3 pi on 4. And you'll end up having a third one brought in at 11 pi on 4 to fit into this domain. And so this is what your function would look like. Noticing, so you would graph your vertical asymptotes, graph your x-intercepts, and create the tan curve, so to speak, and then consider your endpoints. That you won't have had another x-intercept yet. You can imagine that that would happen in the negative region, and off to the right, you will have had an x-intercept, but you won't have hit the next vertical asymptote. Okay? And then this example here, tan of 2x, thinking about what changes have happened there around that 2, thinking about the period, and look at our domain that we have to take it into account. So always start thinking of traditional tan, where that lies, and that your period's going to have changed. So instead of the tan shape happening in a space of pi, that exact same shape will happen in a space of pi on 2 because of that factor of 2 there. So we call that horizontal dilation with a scale factor of 1/2 because it's 1 on 2, it's that 1 on b, and our period is pi on 2. Thinking about where your vertical asymptotes are now, and you have to consider it in terms of that domain. So we're going to have vertical asymptotes within that domain at pi on 4 and 3 pi on 4, and in the negative region. Those x-intercepts, well, the first one will always stay the same at 0, and essentially one way of thinking about it is in between one period, the x-intercept is halfway. So that could be helpful to think of. And here is what your graph would look like. Noticing the endpoints of negative pi and pi, they're also x-intercepts. Okay, the next video in this series is 7E.1 and 2 for trigonometric equations, graphing them graphically and using technology. Thank you.